Greetings! Welcome to Electronics2. I am Razavi. After I produced the first lecture series on Electronics1, I received thousands of emails from people who have watched those videos and were interested in Electronics2. So here we are, and this is our first lecture. So today we will embark upon a new journey together, studying interesting and new circuit topologies and concepts that will advance our understanding and our knowledge so that we can attack and handle larger circuits, more interesting and more complex circuits, and more real-life applications. Today, I would like to start with some introduction to this course, what this course will cover, and how it builds upon the concepts that we learned in Electronics 1. And then I will go into the first new circuit topology that we will study, namely the Cascode. The Cascode topology can be used as a current source or as an amplifying stage. And in each case, it has some very useful properties that we would like to study here. Okay, so the first question is, why do we need Electronics 2? And why was Electronics 1 not sufficient for what we want to understand in real-world applications? All right, well, let's just make a table of what Electronics 1 covered and what we are hoping to cover in Electronics 2. In Electronics 1, we were sort of getting our feet wet, just learning how to walk, so to speak. And we started with some basic concepts, such as the physics of bipolar and MOS devices. So we studied how these devices operate, how electrons and holes move through these devices and generate a current in response to voltages applied to the device. So we talked about bipolar and MOS physics. And based on that physical understanding, we developed models, electrical models for these devices. And in particular, we had large signal and small signal models. So for example, for a MOSFET, the large signal model in the saturation region is just a simple quadratic equation that relates the drain current to the gate source voltage. So we studied these models and we were able to use them. For example, we were able to use small signal models in the study of amplifiers when the input signals and the output signals are small. So we talked about amplifier stages. So we saw three basic amplifier stages in each technology, in bipolar and in CMOS. In the bipolar case, it was the common emitter stage, the common base stage, and the emitter follower, and then their counterparts in CMOS technology. And in doing so, we also learned the importance of biasing. We saw that each of these devices has to be biased so that it provides some transconductance, and as a result, it provides some gain. Without biasing, the device would be dead, so we would not have any useful characteristic from the transistor. We also learned about current sources, and we saw that we could build current sources out of MOS devices and bipolar devices. So that was also very useful. Current sources are used extensively in many different circuits, as we will see throughout this course as well. And one other important concept that we wanted was degeneration. Degeneration applies to the emitter of a bipolar device or source of a MOSFET, and as a result of that, the output impedance goes up and some other characteristics change. So we also wanted to learn that. Okay, of course, we also talked about diodes and diode circuits in addition to all of these. And finally, we wrapped up with op-amps, and we saw that op-amps can be used to build interesting functions such as amplifiers, integrators, differentiators, summers, etc. All right, Now, in Electronics 2, we will introduce some more advanced circuit topologies. So first, that's what we will do. So advanced circuit topologies. And in particular, we will talk about the cascode structure. So cascode, not to be confused with cascade. The cascode structure or geometry or topology, cascode structure. Then we'll talk about current mirrors, another important and useful concept, current mirrors. And then another beautiful invention, the differential pair. Each of these circuits has been around for decades, and they are still used today in most applications because they have so many nice properties. So we want to explore these circuits and see what they do for us. Okay, now in addition to these, we also want to explore some interesting concepts that prove important in practice. One of which has to do with speed limitations. If I am given a circuit, how do I know how fast it can operate? Meaning, for example, what's the highest frequency that I can give it? If I'm claiming that it's an amplifier, can it amplify a signal at 1 megahertz? Maybe. How about 1 gigahertz? How about 10 gigahertz? At what point does it not amplify anymore? So those are the speed limitations of these circuits that we want to quantify. And in that respect, we will study what we call the frequency response. Okay, the frequency response allows us to determine how fast the circuit can operate. Okay, and finally, we will spend a lot of time on another critical concept, namely feedback. And circuits that are built using feedback, so we call them feedback circuits. Feedback is a very general concept applicable to not just circuits, but many domains of engineering, even bioengineering systems or biomedical systems. But in addition, we want to explore how feedback can help us design better circuits. And we'll have to see what we mean by better circuits. So that's a significant concept that we will spend so much time on in this course. Okay, so you can see that these circuits and concepts build upon what we have learned here. Without these, we will not be able to proceed here. So if you are rusty on some of these concepts, I suggest that you go and first refresh your memory about these before continuing with this course. Okay, very good. Now, before we jump into circuits and analysis and so forth, I wanted to just take a step back and see why we say that this knowledge is not sufficient in understanding many of today's circuits. So I want to show you some examples. And these are relatively complex circuits, and at this point, we don't really understand how they work. And that's okay. I just wanted to show you that these circuits are realistic situations that we have to deal with. And one is, for example, the 741 op-amp. Remember that we said an op-amp is a black box with 2 inputs and 1 output, right? You can buy this op-amp. It's called the 741, a classic design. That comes in a package with 8 pins. And if we go and look at the internal circuitry of this op-amp, this is what we see. So, of course, you would expect that the input is on the left. Usually that's our convention, right? The input is on the left and the output is on the right. So the input is over here. In fact, you can see the non-inverting input and the inverting input, just like here. And the output is out here. But then what's going on? There are lots of devices here. Can we recognize any of the circuit topologies that we saw in Electronics 1? Well, there is degeneration here. Okay, so that's good. Then what is this device? What is this device? This device is a diode connected transistor. Remember we said if we connect the base and collector of a bipolar transistor together, the resulting two-terminal device operates as a diode. So we have that here. We don't know why we have it here, but it looks familiar. Then how about at the input? What can I say about this transistor? The signal goes to the base, and it looks like it's coming out of the emitter. So that's something we would call an emitter follower. And then this one, the signal goes to the emitter, comes out of the collector. That's something we would call a common base stage. Okay, so that's interesting. And so if we go around, we might identify certain things, but we are still pretty far from understanding how this whole circuit operates. Okay, so that's one example. Similarly, in CMOS technology, you can look at another op-amp. It's an op-amp from this paper in February 1999, and same story. Okay, so we have an input somewhere. So the inputs are here, V in plus and V in minus. Minus sign has been forgotten. And the output is here. The output is right here. And we really don't know what's going on here, right? What are these things? This circuit is symmetric. It does something. We don't really know what it is. We can see a diode-connected device here. Again, the drain and the gate are connected. So that's a diode-connected MOS device. We don't exactly know what it's doing, but it's there. Then this NMOS device receives a signal at the gate with the source grounded, and the signal comes out of the drain. So this is a common source stage. So that's not bad. But of course, there's a lot of stuff here. So we have to go farther, analyze more circuits, understand new circuits before we can understand something like this. And the story continues. So here's another example of what you could see in practice. This from this paper. So again, we have these stages which we haven't seen before. It's sort of a symmetric stage around this point, around this axis, and then with lots of interesting things, inductors and resistors. Here again, we have the same type of stage, a different stage, two transistors that are cross-connected. We don't know what that is, what it does, etc. So these are used everywhere. And we need to understand more and more, discover more and more circuits so that we can understand these more advanced topologies. Okay, so hopefully by the end of Electronics 2, we can come back to these and have some understanding. Maybe not 100%, but at least a good appreciation of what these circuits do. Okay, so with that said, we can now jump into our first circuit. And the first circuit is the Cascode topology. So we're going to talk about the Cascode current source. As I said, the Cascode can operate as a current source or as an amplifying device. So first we consider it as a very simple constant current source and see what it does. Okay, well, we have to take a step back and remember what a current source is anyway. So let's just talk about that for a moment. So an ideal current source looks like this. We have a symbol for it. We give it a certain value. Let's say it goes to ground. And the definition of this current source is one whose current is constant and independent of the voltage across it. This voltage can go from minus infinity to plus infinity, and this current is always I1 and it's always in this direction. That's the definition. So how would I test this to see if it's a current source or not? Well, I put in a box. So here's a two-terminal device in a box, and I apply a voltage from outside to this box. Let's call that VA. It's a variable voltage, so just a battery, but variable. and I measure this current, IA. And what I expect to see is the following. As VA goes from minus infinity to plus infinity, IA is always constant and is always equal to this value, I1. Okay, very simple. The slope of this characteristic is 0. It's a flat line. Okay, so that's what we mean by an ideal current source. All right, so now you go to a store and say, I would like to buy a current source, and they have no idea what you're talking about. So we have to build the current source out of devices that we already know. For example, out of transistors. So let's do that. And I'm going to start with some observations here. So let's build a current source. All right, so let's build a current source. Okay. All right, how do we do this? Let's change the color of our pen to, for example, red. Well, we know that, for example, a MOS device in saturation can operate as a current source. So here's a MOS device. It needs a certain gate source voltage to turn it on. So we put a battery here. We call it a VB1. And we say this device, we can put it in a box. This is ground. And we can think of this as a current source so long as this MOS device is in saturation. So we're going to write saturation here to remember that's the case. And this is M1. Okay, so how do I test for this to be a current source? The same as before. So I'm going to apply a voltage source from outside, call it VA, between these two terminals, and measure this current IA. This is a variable voltage, and I would like to see how IA varies as a function of VA. Okay, so IA as a function of VA. All right, well, we know that the current source is not ideal. In fact, the current is not exactly flat. It has some slope to it. Why? Well, this is because as this voltage varies, this drain source voltage varies, and we have channel length modulation, as a result of which this current changes. And that's the result of channel length modulation, which means the channel length modulation coefficient, lambda, is not 0. Okay, if it were 0, we would have this. Now that it's not 0, we have that. Okay, why is my pen acting up? Lambda equals 0. Okay, so then that tells us that we have this situation for when channel length modulation is present. All right, but we also know something else. As this voltage goes down, with the source at ground, at some point the circuit completely becomes bad, meaning it's not a good current source anymore, right? It goes like this suddenly, right? Why? Because we leave the saturation region once this voltage is too low. So at some point we enter the triode region. So this is the triode region, and the MOSFET is no longer acting as a current source. And we know at what voltage that happens. We know that if the drain voltage drops below the gate voltage by one threshold, we are at the edge of saturation and triode region. So if this gate is called VB with respect to ground, then the drain has to be VTH below VB. So this would be VB minus VTH. So once the drain falls and it goes past this point, the device goes to the triode region. We don't have a good current source anymore. Okay, so we see that there are two limitations in this circuit. Number one, the output current is not flat, even in saturation region, because of channel length modulation. And number two, the voltage range between here and here, across which the device is a reasonable current source, is limited. It cannot go all the way to zero. See here, we allowed VA to go to zero, even negative values, but obviously here we cannot do that. This voltage can come down and down to up to here, but then past this point we cannot go because the device is not a current source anymore. Okay, so remember these two limitations. Okay, now another method of quantifying how good a current source this circuit is to look at the small signal model of the current source. So let's draw the small signal model of M1. You remember what it looks like, right? We have the gate and the source. So the source is grounded. We have a dependent current source, which we call GMV1. V1 is the voltage, the small signal voltage between gate and source. And then we have the output resistance of the device. And we would like to find the output resistance of this current source, the small signal output resistance of the current source. Okay, well, the gate is sitting at a constant voltage. For small signal analysis, this becomes AC ground. So this becomes AC ground because it does not change with time. Okay, so that means that V1 is between ground and ground, so V1 is 0. If V1 is 0, this one is 0. A current source that's 0 is an open circuit, so this is gone. All we have is RO. So this circuit reduces to just a simple resistor to ground, RO. So obviously R out is equal to RO. Okay, so the small signal model of the current source tells us that it has a finite output resistance, and that output resistance is given by the RO of the transistor itself. Okay, great. So far so good. Now the question is, how do we improve this current source? And that's how we will eventually arrive at the cascode structure. Okay, so the next observation, number 2, is how do we improve this current source? Now exactly what do we mean by improve anyway? Well, by improve we mean how do we have a higher output resistance? So here we got RO, and RO has some limitations of its own. Is there something I can do to this circuit so that the output resistance will be higher than RO? It will become a better current source. The ideal current source has a flat line here, 0 slope, so we would like to make the slope smaller and smaller towards 0. Well, we know one trick from Electronics 1, and we're going to start from that trick, namely degeneration. So remember how this works. We take the transistor of interest, M1, that transistor, and we place a resistor in series with the source terminal. So here's the resistor. This is called the degenerating resistor. Okay? And what we are hoping is that this whole thing now has a higher output resistance, meaning that its characteristic also has a flatter response here than this. So if I apply the same test, a variable voltage from outside, VA, and measure this current IA, what I'm hoping is something like this. So here's VA, IA versus VA. So when we didn't have degeneration, we had a certain slope like this. Now with degeneration, we should get something better than that, right? So it's something like this. So this case was RS equals 0. This is RS greater than 0. Okay, so that's the hope that we have here. We will analyze it a little more and see, but degeneration is one step towards increasing the output impedance of the current source. All right, so let's try to see if that's true. And for that, we will resort to our small signal model. So from a small signal analysis of the degenerated MOSFET in Electronics 1, we have an equation for the output resistance. So this is what we computed in Electronics 1. If this is RS, and what we did is this eventually goes to some sort of battery, so it's constant and becomes AC ground for small signal analysis. And we are interested in this output resistance to see how it compares with what we got here. Okay, so we know the equation for this output resistance from Electronics 1. This is how it goes. It is equal to 1 plus GM, the transconductance of this device, times RO, the output resistance of this device. The whole thing multiplied by the degenerating resistor plus RO. This is what we got from Electronics 1. You might also remember that GMRO has a name. It's good to have that name. It's called the intrinsic gain. It's just a name. It's sort of a fundamental limit to how much gain we can get from one transistor. And GMRO is in the range of 5 to 10 these days. Okay, so indeed, the output resistance has gone up. You can see that previously we had only RO. Now we have RO plus something, and that something could be substantial. We have some RS here, we have some 1 plus GMRO here. Let's say this is about 10. So we take 10 times RS and add it to RO, so the result will be greater than RO. So that's not bad. Okay. Well, unfortunately, this doesn't come for free. Remember, we had two limitations here. One was this slope not being 0, and the other, the fact that there's a lower limit beyond which the current source collapses. So let's go and examine this lower limit in this new case and see if it's the same or not, right? We improved this limitation, but what happened to this limitation? All right, so let me change the color of my pen to maybe blue. Okay, so what I would like to do is understand, now that we have this RS, at what point will this collapse, right? What is this voltage here? How much voltage can I tolerate? What's the lowest voltage I can have at the drain before the current source collapses and its output impedance suddenly falls? Okay, well, what we know is that a MOSFET begins to go into the triode region when its drain is below its gate voltage by one threshold, as we saw here, right? One threshold below. So the question is this gate voltage the same as this gate voltage in the previous case without degeneration or not? Let's assume that the current, the bias current that we have is the same. And let's assume that the transistor dimensions are the same. So that means that this VGS has to be the same as this VGS, right? Because they have the same current and they have the same dimensions. So obviously this voltage, if I have a battery here, cannot be the same as this voltage because this new voltage is equal to VGS plus this voltage, right? KVL. So this has to be equal to this plus this. And how much is this voltage? It's Ohm's law. So we have RS times the current through this. So this voltage drop is equal to RS times ID. So the gate voltage has to be VGS plus RSID, right? That's given. There's no way around it. Okay, so this voltage with respect to ground is VGS plus RSID. And remember VGS, previously we called it VB1. Sorry, this should be VB1. So we will call this VB1. So that's VB1 plus RSID. So what we see is that the gate voltage is now higher by an amount equal to RSID, which means this drain cannot come down as much as before. The voltage at which this current source begins to collapse is now given by VB1 plus RSID, and then we subtract from it a threshold voltage, right, minus VTH. So the difference between this characteristic and this characteristic is that the breakpoint, so to speak, is lower in this case than in this case by an amount of RSID. So what we have sacrificed as a result of degeneration is this voltage range. This voltage range could come down, could include all the way to VB minus VTH before, VB1 minus VTH, but now it can come down only to VB1 plus RSID minus VTH. So we have lost an amount of RSID in the voltage range that we can tolerate across the current source here. Okay? All right. So now, in order to increase the output resistance of this device, this current source, we could try to increase RS, right? You can just increase it and increase it. But the problem is that as RS goes up, RSID goes up, this collapsing point moves this way. So we have a more limited range for the voltage that this current source can tolerate at the drain. So what we are looking for is a device that can degenerate but must not satisfy Ohm's law. Okay, so the current across in the device and the voltage across the device should not be related by Ohm's law. And we know that a MOSFET operating in saturation is such a device. It doesn't satisfy Ohm's law. So let's go ahead and do that. So that brings us to the cascode current source. So that's observation number 3, cascode current source. Okay, so I'm going to take this device, which I called M1, and degenerate it by another transistor. Each of these has its own gate voltage, etc. So this needs a gate voltage, VB1. This needs a gate voltage, VB2. These are, in the simplest case, just batteries connected to these to ground, right? But that's okay. And this structure overall can give us a current source that will have a higher output resistance. So let's analyze that and see. Okay. So I'm interested in this output resistance here. And we're hoping that this cascode structure, 2 transistors connected like this, provides a relatively high output resistance. Definitely higher than a single MOSFET. Okay, how do I calculate this output resistance? This topology we have not seen before. So do I have to write the small signal equations for it, draw the small signal model for it? Well, no, we have enough knowledge from even Electronics 1 to be able to analyze this. Why? Well, let's look at M2 first. So in fact, for that, I'm going to change the color of my pen again to green. Does this look familiar? The gate is connected to a battery, the source is connected to ground, a drain is available, right? Well, that's just this, right? And we saw that the small signal model of this structure just RO. That's it, there's nothing else. So I can replace this whole thing in green with a resistor equal to RO2 from here to here, the output resistance of this transistor, because that's just what came out of here. What we are looking at is M2. M2 has the same role as M1 here, has the same small signal model, same output resistance. So I can simply say that this circuit really looks like this. I have M1. The gate is at AC ground. We're doing a small signal analysis. And the source of M1 connects to this little circle here, which is just RO2. And I am interested in this output resistance. Okay, so now can I analyze this? I don't need to draw the small signal model, right? Because this circuit is exactly like this circuit, except that certain names have changed. We used to call this RS, now we have called this RO2. So I can use the same expression, I just have to be careful with the indices, with the subscripts. So GMRO was GMRO of this transistor, which is called M1. So this would be GM1RO1. RS here has become RO2. So this has to become RO2. And this RO is the same as this RO, which belongs to this transistor. So that should be RO1. So I'm going to just write it out. So we say Rout is equal to 1 plus GMRO of this device, GM1RO1 times the degeneration resistance. The degeneration resistance is RO2 plus the this resistance, which is this resistance, which is this resistance, which is RO1. So that is the output resistance of the cascode structure when it's acting as a current source. Okay, is this a high number? Well, we can simplify things and see. Let's assume that GM1RO1 is much greater than 1. Okay, let's also assume that GM1RO2 is much greater than 1. So the GM of this transistor times its output resistance is much greater than 1. The GM of this transistor times the output resistance of this transistor is also much greater than 1. These are reasonable approximations. So when we do that, this comes out to be, we have GM1, RO1, RO2 only. So we have GM1, RO1, RO2. And that is an interesting result. What does it tell us? This is the fundamental property of the cascode, and we need to understand that very well. Okay, it says that the output impedance of the circuit is approximately given by the intrinsic gain of this device, GM1RO1, times the output resistance of this device, M2. All right, so I repeat. The output resistance of the cascode is approximately given by the intrinsic gain, GMRO, of this device times the output resistance of this device. Okay? Of course, if we are not happy with that approximation, we can always go back to this equation. Okay, so this is the beauty of the cascode structure. It gives us a pretty high boost in the output impedance, right? So if you have one resistance of some amount, then you have GM1RO1 or GM1RO2 multiplied by it, so we get a factor of 10 increase in the output resistance. That's pretty good, right? So that's the beauty of the structure. Okay, now I would like to point out 3 properties of the circuit. So number 1, both of these devices have to be in saturation. So it's important to understand that. Let me change the color of my pen again so that no, not this one, maybe this one. Okay, so they both have to be in saturation. If one of them is not, then all bets are off. We cannot use these equations, right? Remember that for each of these devices to have proper transconductance and output resistance, they have to be in saturation. Okay. Property number 2. In this structure, we call M1 the cascode device or the output device. And we call M2 the degenerating device. M2 degenerates M1, so we call M2 the degenerating device. Obviously, these are very different transistors, they behave differently, right? So, what we observe is that the source of the Cascode device is connected to the drain of the degenerating device. That is the only allowable Cascode topology. If this source happens to be connected to another source, that's not a Cascode, okay? So this source has to be connected to the drain of the degenerating transistor. All right, so that's second property. Okay, the third is the following. We arrived at the Cascode by starting with M1 and trying to degenerate it by M2, okay? And we saw that, okay, the output impedance went up. Alternatively, I could have said the following. I could have said, I have a transistor, the one in the green circle. I have a transistor M2. And M2 has a certain output impedance, RO2. And I'm not happy with that output impedance. I want to increase it. So what I'm going to do is insert a transistor on top of M2 to increase the output resistance considerably. So originally I had only M2, then I inserted the Cascode device on top of it, and the final result is this resistance. Okay? Of course, these are equivalent, but each of them gives us additional insight. So in one case, we say M1 is added on top of M2. In the other case, we say M2 is added below M1, right? Even though it's really the same circuit and the same function. Okay, so this is the basic structure that we have for the Cascode. And let me make sure that we have covered everything that we wanted to say. All right. Now, in practice, we might choose M1 and M2 to be identical or not. It just depends on the situation. In most cases, they are identical, meaning that they have the same width, they have the same length, and of course, they have the same current. The bias current just flows from the drain to the source of this device, and then goes to the drain of this device, then goes to the source of this device. So they have the same bias current as well. All right, so I would like to finish this lecture by posing a question to you, and I will answer that question next time. Here's the question. So maybe I'll try to write it here. What happens to R out okay, what happens to this R out that we just found? You can use the approximation that we have. If the width of M1 and the width of M2 are doubled. So if W1 and W2 are doubled. Sorry, I don't have room here. I'm trying to squeeze everything here so that you can see. Okay? So we assume that the transistors are identical to begin with. They have the same current, same W, same L. And then we go in there, and without changing the current, we simply increase W. Okay? So you can say that ID is constant. Okay? We keep the drain current constant, but magically we increase the width of each transistor by a factor of 2. And what we would like to know is what happens to this output resistance. Of course, you can consider other cases as well. For example, if we double the width of each transistor and we double the bias current of each transistor, so ID is also doubled. That's another scenario, and you can consider that scenario as well and figure out how the RO, the output resistance, changes. So there are different possibilities, but we are interested in only one possibility as far as this question is concerned. So think about that until the next lecture. In the next lecture, we will continue to look at the Cascode current source, and go to bipolar technology as well. And then we will move on to using the Cascode structure as an amplifier. And we will see that it also has some beautiful properties in that respect. I will see you next time.